Hello everyone, it's Josh Rebels. I'm back again with another video. Today we're going to talk about what is pH. So the pH scale ranges from about 1 to 14, and on this scale, a value below 7 indicates that the material that you're testing is an acid. A measurement above 7 indicates the material is a base. And if you get a reading of 7, that means your material is a neutral. And so we rely on both acids and bases all the time. For example, the stomach acids used during digestion are extremely acidic, while hand soap, being basic, is helpful for hand washing. So the pH of something is typically measured with either a pH paper that has a color scale attached to it. And so you dip the paper into your material, and the color change indicates what the pH value is. And similar to that is universal indicator solution, which you just put a couple drops inside of a fluid. The fluid then changes colors, and that will tell you your pH reading. Or for more exact pH measurements, you can calibrate a pH meter. And so in our unit on ocean acidification, we completed some pH experiments using a homemade indicator. Now, it's important to note that not all indicators showed the same color when they're representing a pH value. So when using red cabbage juice as an indicator, the green color here represents a basic solution with a pH of about 10, instead of a neutral reading of 7, which is usually the case whenever you see green using a universal indicator solution. And so using the red cabbage juice, we can see that the color will shift towards an elegant yellow for more basic solutions, and acids will shift the solution from its original color of purple to a pink and then to even red. So if you want to use the red cabbage juice indicator, follow the directions here or use my video where I demonstrate how to make and also use the indicator. So now you might be wondering how this indicator works. You can see these structures are very similar chemically. That is, they have all the same atoms and they are connected in all the same ways by chemical bonds. The difference here is that some atoms have electrons that are not stabilized in their orbit. And so therefore, they move around to different atoms and shift the bonds within the molecule and can resonate from one molecule to another back and forth effortlessly. So these slightly different molecules of anthocyanin are called resonance structures. Now the pH of a solution can favor one particular resonance structure over the other, and that forces the electrons to be localized around a particular atom and to force it into a particular resonance structure. You can see how in the red structure, there is an electron around this oxygen atom. And then on the violet structure, it's not there. Whereas the double bond has formed between these two atoms, and it has shifted from this location in the red structure. And so red cabbage juice is a good indicator because it has multiple resonance structures, and each of those provide a different color for each of the pH readings. Now, the different colors are generated when a particular structure exists because the light that interacts with the molecules behaves differently based on the structure that is predominating in the solution. And so when we see color, we are seeing a particular wavelength of visible light that is reflected from a molecule instead of being absorbed or transmitted through it. Visible light, when all wavelengths exist, is seen as a white visible light beam. Now, if you separate that light through a prism, the refraction of the light causes the light to bend to different degrees. This separates the colors out of the mixture of light into their unique wavelengths, and each of those wavelengths is associated with a specific color of visible light, such as red, yellow, or violet. So to cause that change in color, again, we need all of the molecules of the indicator to be in an environment where they prefer a particular resonance structure so that the molecules then reflect the color that will indicate the pH value that we have. And so this is done when the solution becomes either acidic or basic. And so let's take a look at how a solution can become acidic or basic. This particular reaction that I'm going to show you is a chemical reaction known as the ionization of water. Although it occurs all the time in every sample containing water, this reaction actually only happens approximately once in every 10 million collisions. And so what will happen is the water molecules will collide with sufficient energy so that one of the hydrogen atoms is abstracted and attached to the other water molecule. This creates a hydronium ion and a hydroxide ion. Because the electrons are no longer balanced on the molecules, the chemical species become ions, which are positive and negative charged substances. And so this allows for an attraction between the ions and causes them to be able to come back together and collide once again to return back to their original water molecules. Hydronium, the positive ion, is responsible for making a mixture acidic, while hydroxide, the negative ion, contributes to making a mixture basic. Now, in a system containing only water molecules, the amount of hydronium and hydroxide are equal, which makes it a neutral substance. However, when one outweighs the other is when there is either an acid or a base. pH is a measurement of how many of those acidic hydronium ions are in the sample. And so the mathematical expression for calculating pH is the negative log of the hydronium concentration. So for example, a sample with a proportionally large amount of hydronium will have a lower pH and indicate an acidic solution, while the less and less hydronium in that same volume of solution means that the concentration of hydronium is also less and less. And so when there is a lower concentration of hydronium in the solution, then the solution will be more alkaline or basic and have a higher pH value. And so you can see that in these example calculations. Whereas here the concentration is highest at 0.001 molar hydronium molecule or hydronium ions. And when we plug that value into the formula, we get a pH value of 3. Whereas here we're having less hydronium molecules, and so our concentration is lower, and we get a higher pH. And then the lower the amount of hydronium in the mixture, the higher the pH is, and the more basic it is. Okay, so pH values are determined on a logarithmic scale. This means that it is not a linear scale, which is typically the common way we think. You can see here on this number line that only the powers of 10 are spaced out equally. So we go from 0.1 to 1 to 10 to 100. And so this is what we mean by logarithmic scale. We use a logarithmic scale because it allows for us to take a wide range of numbers, such as on the pH chart, where we go from 100 trillionth all the way up to a pH reading of 1. And we try to scrunch all those values down to a size close enough that it's usable and more convenient to view on a chart or graph. And so what this really means is that a single change in one pH value is actually a big change in hydronium concentration. Each change in pH value is a 10-fold change. And so remember from the ocean acidification video that the ocean's average pH has been 8.2. So even if the pH only changes one pH unit to 7.2, the concentration of acidic ions has changed 10 times as much as it was originally. Now also keep in mind that even though humans can tolerate the ocean's pH in wider ranges, the important organisms needed to sustain the food web in that ecosystem have a much smaller gap of tolerance to pH changes. For example, crabs, snails, and mussels, which are the basis of many food chains, can't tolerate even a pH of 7, neutral 7, to survive. Also remember that the dissolving of carbon dioxide from Earth's atmosphere into the ocean can cause a change in pH. The first reaction of dissolved carbon dioxide in water produces carbonic acid, which can further react to produce a hydrogen ion and bicarbonate ion. Now, the hydrogen ion is the acidic ion that forms hydronium naturally in the water. Essentially, the hydrogen ion and hydronium ions are exactly the same. Therefore, we often just call pH the negative log of the hydrogen ion concentration. Try out the ocean acidification experiment by using the tutorial video also on this channel. In the experiment, I added carbon dioxide by exhaling into the indicator solution. When looking at the color change, you can see that although a slight color change from purple to pink indicates a change in pH from 7 to 5, this is actually 100 times more hydrogen ions in the solution than before. However, the reactions are reversible and will behave according to their equilibrium constants. So to create a change like this, I had to exhale about 100,000 times more CO2 molecules into the solution. Now, of course, over time, the equilibrium will shift the products of the reaction back to the reactants and allow for CO2 to outgas and return the solution to its original color. Check out that video and learn how to try out the experiment for yourself. And so with my numbers that I used in calculations, I determined the following predictions. The first is that since the ocean's pH has dropped from an average of 8.2 to 8.1 since the industrial boom, then that means that we've had 14 times more carbon dioxide in the ocean since that time. So experts predict that a change to 7.8 in pH by the year 2100, which I calculated is about 90 times more carbon dioxide dissolved in the ocean. Now, taking a look at this chart, we can see that 7.8 is getting awful close to the cutoff for some of the most crucial ocean wildlife. Now, if you want to learn more about ocean acidification, I suggest that you watch the rest of the videos on this channel. So we've got a whole game dedicated to learning about the carbon cycle and some videos that go along with it that you might be interested in. And of course, definitely check out Ocean Acidification Part 1 and Part 2. And if you're interested in doing the cabbage juice indicator experiments, make sure you check that out. As always, thanks for watching.